Hello everyone, and welcome back to DMG. I work on a lot of small electronics, and one of my absolute favorite things to find is inside a device that we perceive as being boring and mundane, finding a solution to a surprisingly complex and intricate problem that is fascinating, unparalleled, and straight up just bizarre. And that's exactly what I have for you today. Inside this Juliet clock radio is a clock mechanism like I have never seen before. And the way in which it works is actually very simple once you actually look at it, once you start delving into how it works. But to really understand why this is both so simple and so strange of a solution, one has to understand a little bit more history. So today you'll be getting a short rundown of the history of clock mechanisms throughout the mid-1900s, and hopefully by the end, you're just as intrigued as I am at the bizarre little mechanism. So to understand why this and its mechanism are so special, one has to understand first what most clock radios at the time were like. Of course, there were many different styles, but all of them had a radio on one side, a clock on the other, and a cord out the back. Oh wait, there is no cord out the back. Well, that's not too unique. There were some small travel clock radio models, like this one from Rinsey, for example. Radio on one side, clock on the other, no cord out the back. The radio runs on batteries. However, the clock must be wound by hand. And that is the way that most small, portable, cordless clock radios worked for a very long time. At this time in history, it was pretty impractical to run a clock off of batteries, as evidenced by the numerous travel clock radios that use batteries for the radio, but not for the clock. Now there are a couple ways of rotating clock hands, and the ones that you're going to think of will be all using an electric motor. Nowadays, something like this, one would probably expect to find a quartz clock mechanism inside. Like, let's use this as an example. This is a promotional hard drive platter clock from a long defunct storage media distribution company. And on the back, it's extremely simple. It just runs on a little quartz clock mechanism. There's the little motor. So the speed and frequency of this mechanism is regulated by a quartz crystal, and that's why it's called a quartz clock. And the actual movement of the hands is done by an electromagnetic field that's generated by this coil here, the frequency of which is regulated by the quartz crystal. That, however, is not what this uses. So there's another option, a direct drive motor. And that was actually an extremely popular option. The most popular option of a direct drive motor was the Telecron mechanism, which I have an example of right here. The Telecron mechanism was extremely popular and extremely widely used from the early 1900s all throughout the 50s and 60s. However, there are a couple crucial problems preventing one from running this mechanism on batteries. Now, these Telecron mechanisms use a direct drive motor to rotate the clock hands. They take the 120 volts AC from the wall, step it down to 24 volts, and then this is the actual motor. The rest of this, these arms here, are the transformer, but the motor spins at 3600 RPM. It is stepped down to 1 rotation per minute for the second hand, and then 1/60th for the minute hand, and so on and so forth. But of course, there are a couple problems that come with running a motor like this on batteries. First of all is the current draw. Now, this little Juliet model uses 2 C batteries for its radio and 1 for its clock. The C batteries of the era carbon zinc would have held between 3 and 4,000 milliamp hours. This Telecron pulls 2 to 4 watts AC from the wall, and that's very little power when you're talking about AC power consumption. However, a load like that placed on a battery would only last a couple weeks. But the main problem isn't the current draw. It is the type of current required. And the best way to demonstrate this is through another Telecron clock. This is a slightly older Motorola clock radio, as evidenced by the use of tubes rather than transistors. It uses a slightly older model of Telecron rotor, but the design is the same, just a little bit larger, and the concept is exactly identical. Same transformer to step it down to 24 volts. There's the rest of the transformer running along the side. There's the rotor itself. Spins at 3,600 RPM, stepped down through a system of gears, so on and so forth. Now, if you look at the layout of the circuit here, that's where you plug in power, and that's the clock. Well, if this was a DC motor, something would be needed to convert that power from AC to DC. And that something could possibly look like this: a half-wave rectifier, 35W4 tube. But that's funny. If we take this rectifier out and plug it in, so even with the rectifier removed, the Telecron is clearly running. And that is the big problem preventing a Telecron mechanism or similar AC-powered clock rotors from running on batteries. This is not a DC motor that is converted from AC by a rectifier. It's an AC motor. And just as how the quartz crystal's frequency regulates the speed of the motor in a quartz clock, the rotation rate of a Telecron is synchronized with the 60 Hz AC power. It needs 60 cycles a second in order to keep time. That is what it bases its rotation rate off of. So of course, you're not going to get 60 Hz from a battery. So that eliminates the top two choices, quartz and Telecron. So what else could there be? But obviously, it's not wound. I mean, there's a very clear difference on the back here. There's a very clear split between the radio side and the clock side on clock radios that use a wound clock. That split doesn't exist here. It's also clean. There's just the knobs for adjusting the clock and the batteries. There's no separate side where there's obviously a different mechanism, right? So clearly it's not a wound clock. So what's the alternative? It uses the strangest hybrid between two mechanism types that I have ever seen. And there's no better way to explain it than to just show you. Now obviously, this side contains the radio. This other side is the clock. And I cannot even express to you how surprised I was the first time I opened this and saw that clock mechanism. Because it's nothing like I've ever seen before. I've never seen another clock built remotely like this. And I've worked on, I won't say a lot of, but I've worked on quite a few clocks over the past few months, and I've gotten acquainted with the way they work. And this threw me for a complete loop. So I had to open this clock for service in the first place because the battery compartment was horribly corroded. You can see that rust there. So I opened it up to see if the reason the clock wasn't working was the rust in the battery compartment or an actual failure of some component. I went to go wire something straight to the power input of the clock, knowing that it ran on batteries, so I could test it. But this is... You can see it ticking away, actually. You can see the little guy. You can see its little wheel going back and forth. And it's surprisingly beautiful. I've cleaned this mechanism up a bit. I've really scrubbed this plastic clean so you can see the wonderfully unique way in which this mechanism operates. But I'm going to explain to you what's going on here, because without context, it's absolutely meaningless. So this clock is a bizarre hybrid between the quartz clock movement and the clock movement of a wound clock. So in the quartz clock, the rotation itself is driven by this motor here, this little coil generating an electromagnetic field. And of course its speed is regulated by the quartz crystal. This mechanism, although battery powered, is actually a lot more like a wound clock mechanism than any other electronic clock out there. And the reason why is actually pretty simple to understand, but it needs context. It's such a strange solution that you can't just look at it and think, oh, that's how it works. So this clock module, the whole wound clock, I have a near exact replica of right here, and they all work in about the same way. The power is stored in this coiled spring, which is coiled by your winding, but the actual ticking of the clock is driven by this wheel. This wheel with a spring in the center of it, and the spring compresses and expands. And for every compression and expansion, that is one tick. Now the way this works is in almost the exact same way. However, the source of energy is no longer kinetic. It's electrical. But the clock mechanism, you can see it, is extremely kinetic. So how do you convert electrical energy into kinetic energy? An electromagnet and two magnets. You can see here the same coiled spring as you would find on a wound clock mechanism. And that coiled spring, once again, is what times every single tick of the clock. Now this mechanism actually requires an immense amount of energy to start. Here I have a battery that's 1.21 volts. I connect it, and you can see it try. You can see the magnets start to push off of the electromagnetic field that the coil is generating. But that push isn't quite enough. Starting this mechanism is like turning over an engine. It requires so much more power to actually start than it does to continue running. So this will last for months on the same battery, as long as you don't take it out, which is really funny. It'll keep running down to like 0.9 volts as long as it starts at 1.5, because it needs all of the possible current to begin running. Now, of course, in terms of batteries, you can use anything you want. It's not limited to just a carbon zinc battery. There we go. Now it's ticking to life. It starts better at some angles. Now, in terms of batteries, ironically, it's less picky than a lot of quartz mechanisms. A lot of cheap quartz clock mechanisms require carbon zinc battery. They're designed around the higher internal resistance of carbon zinc batteries. A lot of old gear is. Like, that is precisely why carbon zinc batteries are being used in the transistor radio side of this Renzi travel clock. Because a lot of old gear is designed around the internal resistance of carbon zinc batteries, which is a good deal higher than that of alkaline. But this doesn't have that problem, because all it is just an electromagnet. It just needs current. You could run this off of a potato. You could run it off of whatever the hell you want. So that's a pretty nice touch. The radio also doesn't need carbon zinc batteries, which is also interesting. Usually things with germanium transistors sound a lot cleaner and a lot crisper on carbon zinc because they were designed for that battery resistance. This sounds just fine on alkalines. Well, before we wrap up, I'll give you a quick overview of the radio side and also some nice shots, some closer up shots of this clock mechanism. So, obviously, all germanium. They're all in these wonderful little aluminum cans. That's because germanium transistors, which were only used for about 5 or 6 years before they were replaced by silicon, they run a good deal hotter. They're less efficient, and they also have a slower attack and decay, so a bit like vacuum tubes, they're not super precise. I actually really love the sound of germanium transistors. They have a nice warm tone to them inherently, which of course you can't really hear on a radio this small. But 1, 2, 3, 4, 5, 6, it's a 6 transistor radio. Pretty simple. However, I'll show you a picture of the guts of this Renzi, which was obviously just a transistor radio circuit, like a portable pocket transistor radio slapped into that box. This is different. This seems like it was purpose-built to be in this clock. That absolutely giant antenna at the top wouldn't have fit within a pocket transistor radio. And of course, if this was a pocket radio, they would have put batteries within the footprint of the radio. Another interesting thing is this speaker, Alnico magnet, down-firing, sounds very good, and it's actually made by Pioneer. Yes, that Pioneer, the one that you're thinking of. So it's very funny to me that there was once a time where you could get actual name brand speakers of this size in your tiny little clock radios. Anyway, I'll get you some nice closer up shots of this clock mechanism because, well, I just think it's pretty, and I hope you do too. So here you can really see that spring going back and forth, that spring which regulates the speed. And the tension of the spring can be adjusted through this worm gear with a little screw on the end. And you can see that its position is a little bit below its resting position, I suppose, where it would be from the factory. Now, of course, this metal won't perfectly hold its shape forever, so it is inherently a bit imprecise, so you need to adjust the tension of the spring to get its timing perfectly right. It also depends on temperature. It'll run a bit fast or slow, depending on if it's too hot or cold, because of course the metal would expand or contract, depending on temperature. Here you can really see that electromagnet pushing the wheel back and forth. And further up is the wheel that converts the motion from horizontal to vertical. So that's what drives the clock's hand. And on the same shaft as the two wheels with the magnets is it's a little wheel with one pin on it. And it flicks back and forth twice a second. And that's what pushes this gear around. And that's the second hand. That gear corresponds directly to the second hand. The gears that drive the minute and hour hand are deeper within the mechanism. Now, the company that made this clock has a really funny name, All Mess, and you can see it marked on the back there. This actually does have a jewel somewhere in it. I don't know where. There's the view from the top, or this would be from the back of the clock radio. There you can really see that tiny wheel which flicks the second hand gear back and forth. And let me take out the battery so you can see the magnets themselves. And as it comes to a stop, you'll be able to see, there they are. So the wheel has counterweights on the opposite sides to account for the heavier magnets. And you can see on the opposite sides of the electromagnet, there are two little magnets. One is red, one is gray. Of course, that's North and South Pole. I don't know what all of these other electronics inside the clock mechanism are. Further down there are the rest of the gears, but I don't know what this capacitor is for, or what this other capacitor is for, and I don't even know what this is, this little black component there. I do really, really like the aesthetic. I love how they kept the fake wood grain classic look on such a tiny little piece of hardware. But truly, this solid-state cordless clock radio is just a fascinating piece of hardware. So I hope it interested you as much as it did me.